Good afternoon, everyone. Thanks for joining. Today we have Arkajyoti Manna from IMSC Chennai. He will be talking about scattering amplitudes from generalized recursion. Over to you, Arkajyoti.
Hi. Thanks for the introduction, and I want to thank the organizers for this opportunity. So, the title of my talk is Scattering Amplitudes from Generalized Recursion, and this is based on these two papers, which I wrote with Saurabh Ballabh, who is a postdoc at IISER Bhopal. So, let me begin by giving you the motivation behind this work. The basic idea of the recursion relation is to obtain higher point amplitudes in terms of lower point amplitudes. So to begin with, we will consider three particle amplitudes, and then we'll construct using some recursion relation. We'll construct four particle amplitudes, and then we'll build on them. So for massless amplitudes, BCFW methods is the most well-known recursion scheme in which a pair of external massless momenta get complexified. The BCFW recursion method only requires on-cell three particle amplitudes. This is advantageous over the usual field theory calculations using Feynman diagram, which is not obviously recursive, and also the unitarity method, which requires off-shell three particle amplitudes. So now the BCFW recursion works most efficiently when the amplitude is expressed in the Spina-Helicity formalism, which does not involve any gauge redundancies. So I'll describe this formalism in my talk just a moment. For the massive particle, it seems like the advantage of getting rid of extra gauge redundancies is ceased to exist for the massive amplitudes. But nonetheless, the work of Arkaniyam and Huang on Spina-Helicity formalism for massive particles in 4 dimensions shows that there are some interesting consequence of their construction in terms of the Spina-Helicity variables for massive particles, which will invite one to understand the IR deformation of the massless amplitudes. Also, that will also include the UV completion of some theories starting from the massive amplitude of those theories. But I will not describe those aspects of their work. In summary, I'll say that their work unifies the kinematic space of massive and massless particle into a single Spina-Helicity basis. Okay, so in light of this discovery, what we want to explore? So we want to explore the following. First, how democratic is the BCFW type, or in general recursion technique, of complexifying external momenta? Is it possible to derive BCFW type recursion relations by complexifying massive instead of the massless external states? If this works, then we'll naturally ask how powerful and efficient is the massive massless shift over two other possible two-line shifts, namely both massless and both massive deformation. Okay, so let me tell you what is the plan of my talk. So I'll first review the massless and the Spina-Helicity formalism for massless and massive particles in 4 dimensions. Then I'll introduce the generalized recursion scheme. And after that, I'll propose a little group covariant massive massless shift. And then the natural thing to discuss would be the validity of such shifts. But because the proof is a bit technical and lengthy, I'll discuss that at the end of my talk. So after proposing the massive massless shift, we'll simply assume that shift works, and I'll show that how this massive massless shift works in the computation of 4-point amplitude. Okay. So after that, I'll point out one of the advantages of this generalized recursion by computing some certain class of n particle amplitudes, which was not been computed using the usual BCFW shift. Okay. So let me start by giving the review of the Spina-Helicity formalism in 4 dimensions. So for massless particle, we'll start with the momentum 4 vector. So in the momentum 4 vector in the SL2Z representation can be written as a 2 by 2 matrix. Pj alpha alpha dot, where j is the particle index and alpha alpha dot are the spinor indices. Okay, so because this matrix, the determinant of this matrix gives the norm of this vector. For massless particle, the determinant is 0, and therefore the matrix is rank 1. And any rank 1 matrix can be expressed in terms of two spinors, outer product of two spinors, which I denoted by lambda j alpha and lambda j tilde alpha. And for simplicity, I'll denote the lambda to be just angle bracket j and lambda tilde to be square bracket j. So these are called massless spinor helicity variables. So it is well known that for massless particle, the little group is just the ISO2, which is just nothing but the scaling group, and that scaling works on these lambda lambda tilde variable like this. And with to set up the notation which will appear in computation of amplitudes, I'll be using some brackets like this angle bracket, which is defined like this, and the mass square bracket, which is defined like this. So in general, the lambda and lambda tilde are independent variables, but if you impose the reality condition, then the lambda lambda tilde variables are related to each other like this. So under the little group scaling, on the spinor helicity variables, the amplitude transforms like this, where h is the helicity of the massless particle for which the lambda and lambda tilde are scaled with this. Okay. So now let me tell you the building blocks to compute the higher point amplitude. So the building blocks will be the three particle amplitudes. So for massless particles, due to this kinematics, one has constrained the angle and spinor brackets like this. So this says that either the angle bracket is 0 or the square bracket is 0. Hence, the three particle amplitude can be function of only angle or square brackets. And then we'll use the little group scaling like this, and then that scaling will completely fix the structure of the three particle amplitudes in terms of this spinor brackets up to some coupling constraint. Now I have a constraint. I have put a constraint on the sum of helicity because I want to ensure that the amplitude, this three particle amplitude, has a smooth vanishing limit for real momenta in Minkowski signature. Because if we demand reality, then if one of the vanishing of one of the in bracket will automatically imply that the other bracket also 0. So on cell, this three particle amplitude vanishes. And to make sure that limit is smooth, I have put the constraint on the sum of felicities. Okay, so I want to make two comments about this. The amplitude vanishes when the sum of felicities are 0, except for the case of all three scalar particles. And for gluon amplitude, the three particle amplitude with all identical gluons manifestly becomes 0. Okay. Okay, so now let me move on to massive particles. Now for massive particles, the determinant of this 2 by 2 matrix is non-zero. So the rank of this matrix is 2. And we'll so to describe this matrix, we'll just take the sum of two rank 1 objects. So there is a sum going on, and I introduce an additional symbol I, which turns out to be the little group index for massive particles. The little group for massive particles is just SU2. It's a rotational. Okay, and similarly, I will denote lambda as angle bracket and lambda tilde to be square bracket with an additional index coming from the little group. So under the little group SU2 transformation, the lambda and lambda tilde transforms like this, where this W are some SU2 matrices. And like the massless case, I'll introduce the angle and spin square brackets in terms of the contraction of lambda and lambda tildes. But unlike the massless case, the lambda and lambda tilde are related to each other via Dirac equation. So Dirac equation implies that the contraction with P with lambda tilde gives you lambda and vice versa. So this feature doesn't exist for massless case, hence the massive amplitudes can be expressed in terms of either lambda or lambda tilde. Okay. So now let me make some general comments on the scattering amplitude. Scattering amplitude is defined as the inner product of in and out state, where the in and out state are typically consist of one particle momentum states. So these momentum state transform under little group transformations. So naturally, the scattering amplitude is covariant under the little group, but invariant under the space-time range transformations. Okay. So for amplitude with
Why are
massive
you considering
particles,
only one particle momentum state? You mean tensor product of one particle momentum state?
yeah, yes, yeah, exactly. So these are typically, for example, 2-to-2 scattering. You have two one particle
No, yeah, that's
tensor
fine.
product.
Yeah, that's fine.
Yeah. Okay. Okay, so now amplitude in massive particles, we will use the symmetric representation of a SU2 group to label the massive states in order to retain the rotational invariance. Because if you use the conventional representation of SU2, that requires a introduction of a special Z direction to extract the SZ eigenvalues, right? So that will destroy the rotational invariance of this object, amplitude. So we'll use the symmetric representation of SU2, and with that, typically an amplitude with suppose massless particle with pi momenta with helicity h and massive particle of spin s can be denoted by this object. Okay, so h is for the massless particle and I1 to I2s is for the massive particle. Okay, so with that, now we'll talk about the little group covariant transformation. So here I have assumed that suppose I have a massive spin one particle, and then the object will be look like this, and the little group transformation of the massless and massive spinor helicity variables will be like this, and because this whole object is covariant under the SU2 and the little the scaling, then the transformation should look like this. Okay, so this Tj is basically the scaling for the massless jet particle, and it is raised to the helicity, twice of the helicity. Okay, so after that, now we will be discussing the three particle amplitude. So these are the basic amplitude for any recursion to work. So if we have both massive and massless particle, there are many choices to consider the three particle amplitudes. But in this talk, I'll be considering this following type of three particle amplitudes. So the three particle amplitude I'll be considering is consists of two massive particle with same mass and spin s, and they are minimally coupled to a massless particle of helicity plus minus h. So let me explain. So here I am denoting this minimally coupling by saying that if I write a amplitude expression, then in the high energy limit, it should uniquely extract the amplitude that we already know. So we already know the massless amplitude, which is completely fixed by the little group. So this expression in the high energy limit will give you that. So that is the minimal configuration. Okay, and the X factors are defined like this, where this xi is some kind of reference spinor. And the bold-faced spinor products are defined as a symmetric product of spinor products carrying the SU2 indices. So for example, for spin 1, if we have 0.2 square, it will be like this. Okay. So as I said, that in the high energy limit, it should reduce to the known massless amplitude that I have shown here for the scalar case, where I just wrote P2 to be just 2 spinors. And that will give you this structure, which is also coming from the that formula for massless amplitude, three particle massless amplitude. Okay. So now I'll proceed to the generalized recursion scheme. But if there is any question, please stop me anytime.
Yes, actually, regarding your previous slide, can I ask a question?
Yes,
Yeah,
yes.
so this dependence on this reference spinner, does it actually drop out in the end? I mean,
Yes, exactly. So this dependence of entire this X factor will drop out at the end, but if you consider the 4 particle amplitude. Yeah, exactly.
I see. But but then are you saying that the 3-point amplitude of
Yes. So
one massless, two massive depends on the choice of reference spinner?
yes, exactly. So what happens is this 3 particle amplitude, because you asked the 3 particle amplitude, because I am considering both the masses to be same, what happens that due to the kinematics, there will be a factor which requires you to introduce a structure which depends on these 2 particles. So that introduces this X factor. So at the level of 3 particle amplitude, this amplitude is not local. I mean, it has some information. So if you compute the 4 particle amplitude, you will see that when you take the residue at the propagator associated to that channel, it will have the residue at other. But at the end, it will drop out. Yes.
Okay, thanks.
Okay. Okay, so now let me describe what is generalized recursion. So we will consider any n particle amplitude an, and there will be p1 to pn external momentum. So we'll pick one massive pi momentum and one massless pj momentum, and we'll deform them like this, where z is a deformation parameter and q is some null vector. Okay, so now the deformed momentums are complex, and those are constrained by these conditions. So with that deformation, one can see from a simple contour argument that the physical amplitude can be extracted in terms of product of lower point on cell amplitudes. So which I have written like this. So the first term, I am considering the propagator to be massive, and in the second term, the propagator is massless. But importantly, all the sub amplitudes are here computed on cell. So all the sub amplitudes are evaluated at the pole, which I denoted by z equal to zi. So in writing this formula, I have assumed that the amplitude decays at large Z. So in the contour argument, what happens that these terms appears as a residue at finite Z in the Z plane, and there is a piece which associated to the residue at Z going to infinity. So we want to drop that term. So to do that, we'll assume that the amplitude itself decays at large Z, and we'll end up with this formula. So this is a very critical ingredient in to prove these kind of shift actually works. That I'll describe at the end of my talk if I have some time. Okay.
Sorry, just to clarify, this is an assumption that you're going to justify later on, or this just there's no way of justifying this. Yeah.
No. Actually, we prove that these shifts works for a certain class of theory, but I'm saying that that I'll describe at the end of my talk, because it's a kind of lengthy and technical. So
okay,
I'll do that at the end of the talk if I have some time. Yeah. Okay, so let me move on. So diagrammatically, on-cell recursion scheme will look like this, where I have deformed any two adjacent legs, L plus 1. It doesn't matter whether it's, so these wavy lines are for massless particle, and these solid lines are for massive particle. But the deformation doesn't involve any choice of massive or massless particles, as we will be proceeding. But the important thing I wanted to point out is that the deformed leg cannot be attached to the same sub-amplitude. Then the recursion fails. So on-cell recursion method works for amplitude that are forced to exist by consistent factorization given the 3 particle amplitudes. So these excludes theories with contact terms. For example, the lambda 5. Okay. Okay, so now the complex shift of the external momenta should be realized in terms of spinor-helicity space, as the amplitude is a function of these variables. Okay, and it is paramount that the complex shift of spinor-helicity variables obey the little group covariance, as the amplitude we will be considering are manifestly covariant under the little group. So now let me give you the spinor deformation. So we are considering the deformation of the momenta is like that. So Pi is massive particle and Pj is for the massless particle. So in the spinor helicity notation, there will be lambda lambda tilde for each momenta, and we'll choose this null vector to be like this. So if we choose that and demand that these two spinors doesn't differ, then we'll find that the other counterpart must deform like this, the spinor helicity variables. So here J hat is a deformed spinor helicity variable and J is an undeformed version. Plus there's a piece which is proportional to Z by M, and there's some inner product between Ij, and I is contracted because the J spinor helicity variable associated to the massless particle, which doesn't carry any little group index. Similarly, that happens for the massive spinor helicity variables. Okay. So, so this is the massless shift and this is a massive shift. We'll denote such shift as Ij of the type M plus. Okay. So so we have shown that that for Higgs-Triangle theory, the valid shifts are M plus and minus M, and the other two shift doesn't work for this theory to compute the amplitude. Okay. So yeah, is there any question? Okay. So now let me give you an example of how this shift works. So we'll be considering a 4-particle amplitude involving two massive spin-1 particle and two opposite helicity gluons. Okay, and we'll shift the P1 and P2 external momenta, and so these are gluon amplitudes, and we'll be computing only color-ordered diagrams. So with that color ordering and the 1-2 shift, there is only a single diagram. Okay, so the 1-2 shift is defined like this, but if you do the unitarity method, then there's another color ordered diagram where 1-2 is attached to each other. So in unitarity method, we need to consider an extra diagram as opposed to this in this method. Okay. So now the recursion relation with this diagram, the recursion relation dictates that the 4-particle amplitude can be obtained by gluing these two sub-amplitudes, and that is exactly what we will do. So the propagator is S23 hat channel, and using the on-cell 3-particle amplitude that we have already defined, and removing the extra dependence on the internal spinor helicity variable, we'll find the expression to be like this, where these bracketed spinor brackets, these hatted spinor brackets has to be evaluated at z equal to zi, and z equal to zi can be found by simply putting this propagator on cell. So that gives the expression for zi like this. So at Zi, after evaluating all the spinor brackets, the expression, the full 4-particle amplitude is this. Okay. So so far so good, but let me point out one of the limitation of this complex deformation, the appearance of spurious poles. So although we are
actually I had one question.
Yeah.
Can I ask?
Yeah.
Yes. Yeah. So the amplitude that you showed. So actually, weren't this type of amplitude is computed in actually Nima and Utin's paper?
Yes. So they computed. Yeah. So they computed using unitarity method. So what happens that in unitarity method there is another diagram. due to this color ordering.
Mm-hmm.
But in the recursion, we have to do only one single diagram, single channel system. So this is one of the advantages.
I see. And in this case, suppose instead of actually doing this one massless and one massive shift, if you had done a shift of the two massless guys, let's say you shift 2 and 3, then
exactly.
in that case, yeah, I'm just trying to understand whether I mean that shift is simple in some sense, or
yeah, that shift is also one can do, and simple, because we are only considering a 4 particle amplitude, so you have to do a 3-2 shift there. So also the answer you will get is the same. But what I'm saying that I am just giving an example of where this. But I'll give an example where this generalized recursion will work in computing certain class of amplitude, but the BCFW cannot work. So that I will give an.
Okay.
Yeah. Okay. So also, although we are deforming external moment with a complex shift, but the theory of which we are the scattering amplitude we are considering are unitary and local. And unitarity and locality dictates that the tree-level amplitude can have only simple poles in terms of the propagators. But what happens that in the on-cell recursion amplitude, in some intermediate step, you will see that there are some terms which are not looks simple pole, but which are not propagators. To see that, let us consider the 6-point gluon amplitude in this configuration. So there are 2 channels, and this is BCFW shift. So here they took 1, 2 shift, and there are 2 diagrams, and the result is given by this. So apart from all the other factors, this factor doesn't come from any propagator, but it's still there in the BCFW expression. So these kind of poles are called spurious poles, and people have shown that the residue at these poles must vanishes as it should be, because the theory is unitary. And people have also shown that there are some complicated algebra which will tell you that you can get rid of this propagator. But the point I want to make is that the BCFW method cannot do not give you always consistent answer consistent with unitarity and locality. So this is one of the backdrop of the of doing complex deformation of external states. Okay, so as a side comment, I want to say that so its cancellation, the cancellation of this Fourier pole was shown in momentum twistor space by interpreting the amplitudes as a volume of some certain types of polytopes. But these spurious poles appear as spurious boundaries. So those spurious boundaries can be shown as some internal boundary of the polytope, and they will cancel each other. So in the momentum twistor space, one can show that the amplitude doesn't have any spurious poles manifestly. This is just a side comment. Okay, so now I want to point out what is one of the advantage of doing generalized regression. For that, I will be considering 2 classes of n particle amplitudes. Okay, so the first class I want to consider is the following. The scattering of two massive vector bosons with identical holistic gluons. In this case, I'll be considering all positive holistic gluon, and I'll consider 1-2 shift. So with this shift, there are 4 kind of diagrams, and the first, second, and third diagram vanishes. So the first diagram and third diagram, this first and the third diagram vanishes because a single massive vector boson cannot decay into identical gluons. So for the first diagram, this right sub-amplitude vanishes, and the third diagram, this right sub-amplitude, three particle right sub-amplitude vanishes. And in the case of the second amplitude, the right amplitude, which involves purely gluons, but it involves only either all plus LST gluon or one minus LST gluon, but that is that vanishes. So only this last diagram survives. So to compute this amplitude, we have to consider only this diagram. Okay, so the strategy to compute this diagram is the following. So we propose the relation between the n particle amplitude of involving two massive vector bosons and two massive scalars like this. So they are differed by this factor. So this is observed in already in lower point amplitudes, and for higher point amplitude we propose this formula. So this is just this is not new. This is just a covariantization of the relation that has appeared previously in this paper for a particular choice of spin of the massive particle with respect to the common spin axis. So with this relation, we obtain the vector boson amplitude from the scalar amplitude, and the scalar amplitude is already known from a paper appeared in here. And the scalar amplitude is this, and so the vector boson amplitude can be just using that formula can be written like this. Now we'll use the generalized recursion 1-2 shift and the method of induction to prove that this formula is indeed correct. So as I already mentioned that the first three diagram vanishes, we have to consider only this diagram. So we'll be looking at this. Okay, so to initiate the induction, we look at the 4 and 5 particle amplitude, which trivially matches with this expression. For then we'll assume that the n particle amplitude is exactly like this, and compute the n plus 1 particle, which turns out to be like this. So this serves as an inductive proof of this expression. Okay, so now I wanted to mention that although this amplitude can also be computed using BCFWC, but now let me come to the class of amplitude which cannot be computed using BCFW. So here we really see the advantage of the generalized recursion. Okay, so this second class of amplitude we are considering is the same as the previous one, but one of the gluon adjacent to the one of the vector boson is now have helicity negative. So here we consider the 2 to be of minus helicity gluon, and we will use the same class of generalized shift, and with that shift there will be diagrams like this. So although as we are considering only minimal coupling, the extent particle can be either massive vector boson or gluon. But it cannot be, the extent particle cannot be massive vector boson, because you see that if we have massive vector boson, then that is decaying into the opposite helicity gluons. That is also not possible. So the extent particle can only be gluons. Okay. And due to this 2 minus 1 shift, the first diagram gets non-zero contribution from helicity configuration for the internal state indicated like this. The other possible state like minus plus doesn't produce any answer due to this shift. So due to this shift, the amplitude, the 3-point amplitude vanishes if we take this helicity of the internal state to be plus. Okay. So so the amplitude for these all the diagrams can be written in terms of the regression in this form, where the shift I have written like this, and the last diagram is consists of a 3-point amplitude involving 2 massive particle and 1 massless gluon, and the particular amplitude. So this only this the amplitude we have to compute explicitly, but all all the other diagrams involves a subamplitude with only gluons, either gluons or subamplitude with massive vector boson and identical positive holistic gluons. But this configuration that we have already computed in this form. So we'll borrow that result to compute this amplitude. Okay. Okay, so we'll do that. So finally, the amplitude will look like this, where this first sum is over all the diagrams except this there, except the last there. Okay, so that I have written here like this, and the last term is like this. So here I have red colored these two terms because these two terms produces spurious poles starting from n equal to 6. So from n equal to 6, these terms become spurious. So the problem of spurious pole remains following. Okay, so to summarize, let me give the comparative analysis between the BCFW and generalized recursion. So, so the first diagram is where I have done a BCFW shift on 2, 3, and which resulted into two diagrams. But if you look at this second diagram, the left sub amplitude involves the same configuration of external particles that we are trying to compute. So there is a 2 minus attached to this amplitude and all the plus holistic gains. So this amplitude cannot be computed using BCFW, right? But on the other hand, if you do the generalized shift, then all the sub amplitudes are already known. So you can compute this amplitude from scratch using this new recursion. So this is the one of the advantages that we want. Okay, so is there any question? Or I can move to the proof of the generalized recursion.
Yeah, so this spurious pose, right? So how they vanishes in momentum space, I didn't get it. So it's like I can't see any unknown here, so that it can tune up and this guy should vanish, right?
No, actually, to show that in the final expression there is no spurious pole is very technically challenging. So what people usually do is that they compute the residue at these poles, right? And if the residue at these poles vanishes, then you can say that, well, there are poles, but they are not spurious.
Oh, I see, yeah.
Yeah.
Thanks.
In the spinor health formalism, this is the thing. But in some other formalism like momentum twisted, you can see that because the amplitude is expressed in terms of some volumes of some polytopes, and these poles will appear as some in the internal facet of that polytopes. So that's how they cancel with each other. So in that formalism, it is manifest, but in the spinohelicity, it is not manifest.
Thank you.
So, I mean, I joined a little later, so I didn't see the initial part, but still, I mean, you're calculating these, various point amplitudes and so on. What are the checks you have? I mean,
so for example,
give me an answer. How do you like check it again?
Yeah. So for example, So for example, this amplitude that I have computed here. So this is a simple 4-particle amplitude, and I got the result like this. So if you if you do the same calculation,
Feynman diagram, can you check? Okay, 4 point maybe.
Yes, exactly. So you can do the Feynman diagram, but a simple method is to do it from the unitarity perspective, which doesn't involve this kind of shift, right? So if you do the unitarity method, what happens that there is an additional diagram, but if you add the two contributions, you will end up with the same result. So that one of the check, but another check is that if you take the high energy limit, for example, like, so these are massive spin 1 particle. So in the high energy limit, it will be like either helicity +1 or -1. Suppose you take helicity +1, and for this particle helicity -1, then it is a Park-Taylor amplitude, right? So it will produce the Park-Taylor amplitude. I haven't shown how to take the high energy limit here, but okay, maybe for n particle amplitude I have a slide that I skipped. Okay, so maybe I can tell you. So this is an expression for n particle amplitude where I am considering two massive vector boson and all other particles to be Placidistic gluons. So that takes this form, right? And the massless limit dictates that if you have a bolded spinner like this n angle bracket, so in the massless limit, it reproduces only negative helicity massless state, and the angle bracket produces plus helicity. Okay, so here because we have only angle bracket, then the massless particle have to be negative helicity particles, right? In that case, that is a Park-Taylor amplitude, and which reduces like that. And also, this structure directly tells you that if you take plus helicity configuration for any of the massive particle, that will vanish because of this dictionary, right? And which is also true from gluon amplitude point of view.
So these are like consistency checks and so on.
Yes, consistency check, and also, so in our paper there are several consistency check, like not for this one, but for this opposite helicity gluon case, there are n-MHV amplitude which have been computed for this n particle by Barn et al. And we have checked with this specific ordering of our external particles, this result matches with that n-MHV. And also you can do the soft theorem, please. Yeah.
So just to clarify, another point is that since there is another alternative method which gives rise to the same answer, the way that you're doing things, does it have any advantage, maybe conceptual or otherwise?
Yes. So the same answer you will get for this class of amplitude, where you have all identical helicity gluons. But if you have one of the helicity to be flipped, then you cannot do the BCFW. You have to do the generalized recursion helicity, as I have mentioned here. So if you do the so this sub-amplitude, again, identical to this configuration.
And then what would be the checks in this particular case? So, are there any checks?
So the check is that, so in this case, I have one negative helicity gluon. So these massive particles can have both the helicity configuration in the high energy. So you have one configuration.
Hello.
Plus helicity.
Yeah.
Hello.
Sorry, you got cut off. Can you repeat the sentence? Yeah.
Okay. Yeah, I'm saying that in this configuration, because I am having a second particle with negative helicity, these two particles, massive particles, can have both helicity configuration in the high energy limit, right? Because the structure is like that. So if you consider, suppose opposite helicity configuration for the massive particle, suppose 1 minus and nth plus, then it should reduce to the Park-Taylor amplitude. And that exactly happens at this term. So the amplitude is sum over these two terms. So the first sum of these diagrams vanishes in that configuration, but this configuration, reduces to the Park-Taylor. Is there any other question?
Yeah, one more question is, you mentioned this already, but can you just remind me? So when you're applying these techniques, you have assumed that the amplitudes falls off faster than.
Yes, exactly. So, So if that doesn't happen, then this recursion doesn't work. I mean, so in some cases, people have extended this scope by computing explicitly the residue at large jet, but those are very specific and theory dependent. For example, for the lambda 5/4 case, people have done that. But in this talk, I'll consider only amplitude that decays at large jet.
Okay.
maybe I can tell you more about that if I have some time.
Okay,
so
sure.
this is a okay. Should I go ahead?
Yeah. So this from if I calculate this amplitude, that 6-point amplitude that you have shown. So if I can calculate from this one from the Feynman diagram, will it contain the same spurious pole? The residue
No, exactly.
That will be
So yeah. So Feynman diagram, the field theory technique will always take care of the unitarity and locality. So with that technique, you will never have these spurious poles. But in the Feynman diagram technique, there will be several other diagrams you have to consider. So yeah.
I see.
Yeah. So this is one of the backdrop of doing this complex deformation, but yeah, nonetheless.
I see. Okay, thanks.
Okay. Okay, so since I have some 10 minutes, so maybe I can tell you what is the largest behavior. So let us recall that the contour argument is like this. So the physical amplitude can be extracted from the deformed amplitude from this expression and doing the Cauchy's theorem, application of Cauchy's theorem, right? And then what happens that there are some contributions from finite z, which is denoted by zi, and there are some pieces at infinity. So we want to drop these pieces. So to demand to drop these pieces, we'll usually demand that the deformed amplitude itself vanishes at large z. Okay, so but this assumption is far from obvious and not even true in any general theory. Naively, if you look at any Feynman diagram, then it will always scale as z as order z or z equals 0 for gravity and gaze, right? So at this point, the recursion is no way looks to be working, right? But what happens that surprisingly, at least for some helicity configuration for external particles, BCFW shows that. So I have shown that the gaze theory amplitude does vanish at large. For example, if you deform the external spinner of any minus helicity gluon and plus helicity gluon of the bracket spinner and the angle spinner respectively, then it vanishes, it scales at as 1 over z at large z. Similarly for these two combinations also. But there is a combination plus minus for which the amplitude doesn't vanish. So the BCFW shift of this kind doesn't work for the gluon amplitude. So the only allowed shift are these three. Okay. So this can be shown from the field theory perspective like this. So since we only care about the z dependence of the amplitude and all the soft physics can be absorbed into some background. So at a large z, the amplitude can be studied by considering a single hard line suited from the soft background and by looking at the quadratic fluctuation about the background. Okay, so for real momenta, this corresponds to the familiar iconal scattering. In this approximation, the helicity of the highly boosted particle is conserved and shown to be consequence of enhanced spin-Lorentz symmetry. So because of the introduction of constant background, the space-time Lorentz symmetry is gone. But at large z, what happens that some enhanced symmetry arises, which we will call spin-Lorentz symmetry. So that can be realized in this cartoon maybe. So I have considered two scenarios where the large momentum in this case is real. So in this case, this n particle amplitude is just a product of this boosted line and times the soft whatever background amplitude. But if you have momentum which is complex, then one can show that the dominant part is again controlled by this symmetry, spin-Lorentz symmetry. But there are some pieces for which the helicity conservation doesn't work. So the amplitude will be dominantly will be like this single line, but there are some interaction term with the background. So to see this for gluons, so one can consider the Yang-Mills Lagrangian and introduce and expand the gauge field like this, where A0 is the constant background and chi is the fluctuation, and we'll keep terms quadratic in chi and in the Lagrangian, and for that Lagrangian we'll write the amplitude from the vertex factor. So that will look like this. So the first term is proportional to eta AB, and so this term respects this spin-Lorentz symmetry because of eta, but there are some pieces which are denoted by MAB, and all the other pieces are suppressed by 1/z. So this piece is antisymmetric in this AB index. Okay, so this is the amplitude you will get by simply looking at the Lagrangian. Okay, but the on-cell amplitude that we will be considering is obtained by contracting this field theoretic amplitude with the external polarization of a hard particle. So that's what I have written. So H1H2. H1 is the helicity of the external state, boosted state, and the associated polarization is like this. So they are all function of Z. So one can express these polarization in terms of spin helicity variables, and see that after contacting with AB, we will find that the required structure is like this. So this is from the work of Nima Kaplan, but in our case, where we have considered an amplitude with massive vector boson, what happens that in this case, we'll be following the same background field method, but the amplitude we are considering has gluon in the in state, and it will produce a massive vector boson in the out state. So that's the configuration we want to look at because of the massive massless. Okay, so this amplitude is again written by this. So this AAB is coming from the Lagrangian expression and contracted by the polarization. So there are two modes because of the massive polarization tensor. Two of them are transverse and one of them is longitudinal. Okay. So the larger limit of the amplitude combined with the action of word identity acts differently on these two modes. For the transverse mode, we consider the scattering of boosted gluon of a heavy scattering center surrounded by a cloud of soft gluons. So in the pure gluon case, is just a single gluon suited through a background of soft gluons, but in the vector boson case, the background is simply consists of this cloud of soft gluons and heavy scattering center made of vector bosons, which are not for which the external momenta is not shifted. They are low energy. Okay, so the soft background is replaced by this static background, which include a collection of massive and soft massless particles. Okay, so I am just giving you the outline. I am not going into the details. Is that okay? Hello.
Yeah, that's perfectly fine. Yeah, carry on.
Okay. So the dominant contribution to the amplitude at large jet, when the helicity is conserved, the boosted gluon is unchanged. The amplitude is again constrained by the spin-Lorentz symmetry, and the structure will look like similar to this. And again, we'll find the structure. The amplitude decays at large jet. And the longitudinal mode A0 plus is related to the amplitude of massive scalars with gluons via the word identity for the spontaneously broken gauge set. So the longitudinal mode can be essentially treated as the amplitude where the massive particles are replaced with massive scalars. Okay. Now the scalar amplitude vanishes at large Z by simply looking at the Lagrangian and doing the same analysis. We have shown that this scalar amplitude also vanishes. Therefore, this longitudinal mode decays at large Z. So to summarize, we find two classes of shift, M plus and minus M, which lead to consistent recursion as the amplitude vanishes at large Z. But the other two class, the amplitude doesn't vanish. It diverges at large Z for the Higgs triangles. So the values shift are these two. Okay, so I am almost done. To some outlook, we hope that this work will pave the way to compute more tree and loop level amplitude using the generalized recursion relation. We would like to extend the analysis for the n particle amplitude for arbitrary ordering of helicity and external particles. It will be great to explore the usage of the shift in various graviton amplitude. Okay, so yeah, I'm done. Thanks.
Okay, thanks.
Arkojyoti, one question is that apart from this fall off that you assumed, there is no other place that you needed to say anything about what a potential Lagrangian connection is.
No, actually, all this on-cell approach to amplitude actually doesn't require any Lagrangian description. So this proof that I have,
you're assuming some fall off, right? I mean, so that
I'm saying that that fall off. So there are several other resources that, for massless amplitude at least, they have given this large Z fall off simply from the expression of the on-cell amplitude. They didn't consider any Lagrangian itself. I'm saying that although we are giving a Lagrangian distribution, but it is not necessary.
Right. No, but maybe a more well-defined question I have is that suppose I actually added some non-renormalizable operator to, I mean, imagine that there was a Lagrangian description and I added some non-renormalizable operator to the theory, which would potentially spoil the fall-off behavior that you're implicitly assuming, the large Z fall-off that you're implicitly assuming.
Right.
Would that spoil, I mean, for example, in some effective field theory, would your method still work, or can you modify your methods so that they work?
If you have some non-renormalizable terms, like so you're saying some terms which makes the theory non-integrable kind of thing, right?
Non-renormalizable, so higher dimensional operator. So in the standard model, people are all very interested in dimension 5, dimension 6 operators. So suppose you added them. Of course, the theory is not going to be valid at all energy scales, but the theory is valid up to some energy scale. So in such a theory, would you be able to calculate any endpoint amplitude?
But that is related to the structure of the 3-point amplitude actually. So if you have, suppose, a high dimensional operator, so in this examples, I am only considering minimal coupling, but what happens that if you have high dimensional operator, then there are some additional terms and your structure amplitude completely changes.
Potentially it can change. Yes, that is true. It can change.
Yes, yes. Then what happens that in the Lagrangian description of this proof, okay, maybe I can show. So this Lagrangian we have found from the standard Young-Mills. But if you have Young-Mills plus suppose f cubed term, right, hard dimensional operator, then there are additional terms. So then the structure of this amplitude also changes. Yes. In that case also the conclusion of this, what is valid proof or not, that will also change. Yes, you are right.
Yeah. Okay.
Yeah.
So actually, I had one question.
Yes.
Yeah. So using your formalism, so actually, have you tried to explore actually gravity scattering amplitudes? Let's say you have gravitons with a bunch of other massive particles.
Actually, that is what we are currently doing.
Okay. Okay. Good. Oh, it's in our Outlook. I didn't see that. Okay. Great.
Yes.
Okay. Okay.
Any other questions?
Yeah. So since I have your Feynman diagram calculation and this that 6-point amplitude that you have shown. Okay, so they differ by this, right? So by this spurious pose. So
yes.
is that, I mean, so is that this representation that you have shown here, is this one is unique, or you will have to prove that this is whatever you do, you will end up with this exact same answer? So you have
So let me so the appearance of this Fourier's pole is solely due to the complex deformation of the external states, right? But in practical purpose, if the theory is unitary and local, right, then the external momenta cannot be complex, right? So if you do the Feynman calculation, then there are a bunch of other diagrams, but you can add them up, and you will see that the simple pole only occurs at the propagator level. So you will never see the spurious pole appearance. But
yeah,
because
that
we
I
are doing
understand.
this complex
But my question is that your answer is unique. How do you know? That is my question.
Oh, this is not at all unique. This is not at all unique. This is not unique. So this is unique in the sense that if you do the computation in spinor helicity formalism, then it's unique. I mean, it's say in some representation, this is the answer.
I see.
Like this 3-particle amplitude that I considered, right? Okay, so suppose so this is the expression given in terms of the massive spinor helicity variables, right? But if you do the so consider the case of massive scalars, right? It will be just polarization times the moment, right? One of the moment, except for massless moment, but yeah. But in the so apparently they looks different, this structure and the E dot P structure, but you can show that using the expression of X and stuff, these actually reduces to the E dot P for the Feynman diagram. And also you can do the similar things for the vector boson and fermion case. That is just you have to write the external that polarization tensor in a suitable, because these amplitudes are all written in the this Lie group space, but the Feynman diagram calculation will always give you in the Lorentz. I mean, they are Lorentz tensors, right? Basically, mu, nu, and stuff. So you have to contract them with the external polarization to make it scattering.
I see. Okay. Thanks.
Yeah.
Just a general question. I mean, has fermions been done? External fermions?
Can you repeat?
External fermions.
Yes.
Has that been done?
So. Yeah. So for external fermions, the n particle amplitude has already been done by Ochiro, but I must say that I mean, he didn't use generalized recursion, but he used, and so for external endpoint amplitude, there are some result already known from the Behrens-Gale recursion, right? So he used that and used that method of induction to show that the formula indeed works using BCFW type of suit. But it has been already done. Yeah.
Okay, so if there are no further questions, maybe Justin or Orko Jyoti and I can have a quick chat, and the rest of you can leave.
Yeah, sure.